Okay, welcome back. Here we are for lesson 4.2. Let's see if I can zoom in a little bit on that so that you guys can see it. Now remember, this is on a YouTube. This is on a YouTube channel, and so if you want to enlarge it, you need to go to the YouTube channel down at the bottom, click on it, go to actually YouTube, and then you can make it big screen. I think this is just showing up as little screens, although there's something I'm going to try to do on the LMS to fix that, but if all else fails, use the YouTube link and off you go. Otherwise, you're going to be trying to read all those little tiny things, and that's just not going to be fun. Okie dokie. So, scalar equation of a plane. We've spent the last couple of times talking about vector equations of lines and vector equations of planes. Consider the following diagram. This is supposed to represent a three-dimensional shape here. So you've got your plane. You've got direction vectors that are in the plane that are B and A. Okay, so they're actually in the plane. And then you've got this other vector coming up out of the plane, perpendicular to the plane. Interesting, if it's perpendicular to the plane, then it's perpendicular to every direction vector in the plane. So it's perpendicular, and we call that the normal to the plane. So bottom line, what we're doing is we're now going to talk about the scalar equation of the plane. We did talk about the scalar equation of a line. Remember that, and we used the normal to help us with that. We're now going to talk about the scalar equation of a plane. Good news about this is scalar equations of planes are unique, whereas vector equations are not unique. There's an infinite number of different ways to describe any one given plane. Okay. The other thing I'd like you to notice from this is that this sort of looks a little slanted, if you will, a little askew from the XY axis, and that's on purpose. I want you guys to really understand that planes do not have to be parallel to the X and Y axis, or the XZ axis, or the YZ axis, but we can have things that are slanted. Okay? All right. Any vector that is perpendicular to a plane is a normal vector to the plane. So that's just definition. So any vector that's going to be perpendicular to the plane, we're going to call a normal vector to the plane. It's just it's just names. There you go. You can determine the normal to any plane by figuring out a cross product between any two vectors in the plane. Now that should make sense, right? Because the cross product is called the vector product, and it gives you the vector that is perpendicular to two other vectors. So here's vector A, here's vector B. They don't have to be like this. They could be like that, but since they're direction vectors, I can put them together so that they're in this orientation. And then if I take the cross of these, it's going to give me a vector that's perpendicular to both of them. Okay, that's just the property of a cross. So we're going to use that. So, example 1. Determine a normal to the plane with the vector equation 3, 0, 2, direction vector 2, 0, negative 1, 6, 2, 0. Now this is interesting. See that direction vector? 6, 2, 0? All I care about is its direction. I don't care about its length. I could represent that equally as well right now as 3, 1, 0. I could reduce it. Let me zoom in a little bit so that you can see that maybe a little bit more. But this is where we're going to have to start being smart about what we can reduce and what we can't. If I'm only interested in the direction, that's perfectly fine. It has the exact same direction as 602. In fact, if I think about it three-dimensionally, boom, let's do this. Z, Y, X, let's make Z a little bit darker. Z, Z, Y, X. So 0, what was it? 6, 2, 0. So 6, 2, 0 is, let's call it here. Let's make 6 bigger, okay? Do we agree? 6 will be out here, over by 2. That's probably better. So this will be 6, 2, 0, whereas 6, 3, 1 would be here, 3, 1, 0. So I'm going to poll my audience that's sitting here. Does that make sense? Okay, so the direction didn't change. The magnitude changed. So if I'm talking about the direction vector, I can use either one. But you better think. You better think before you just reduce stuff. You better know what you're doing. Okay, so I want to do the cross. Let's see, I'm going to use the fancy pen because I can. So I want to do, let's call this direction vector 1. Let's give it a name. 2, 0, negative 1. Let's call this direction vector 2. And I can use 6, 2, 0, or I could use 3, 1, 0. Obviously, 3, 1, 0 is going to give me smaller numbers. I'm going to choose to do that because, hey, I'm lazy, and I'm going to do things as easy as possible. So if I'm going to do D1 cross D2, I'm going to have the first vector, 2, 0, negative 1, 2, 0, negative 1. And let me move something. It's on the screen for the people that are in the audience, but it's not on the screen for you guys, so let me just tidy something up here to make things nicer for... How's that? We better? You guys can see it better? Yes, Mr. White. All right, that's great. All right, so, and then I'm going to use 3, 1, 0, 3, 1, 0. I'm going to get rid of the first and last. If you don't know what I'm doing, then that's a problem. These are the down products. You're going to take the down products and you're going to subtract the up products. Is that right? Down products subtract up products. So it's going to be 0 times 0 is 0. Subtract 1 times negative 1 is going to be plus 1. So it's going to be 0 plus 1. So I'll make it 1. This will be negative 3, subtract 0. So that'll be negative 3. This will be 2, subtract 0. So that'll be 2. And lo and behold, you have your normal vector. Yay! Now, had I had the 6, 2, 0 in here, I would have got a normal vector that was larger here, but it too could have been reduced. And I'm going to leave that for you to do. So right now, you should pause the video, do your own cross with 6, 2, 0, and see what you get. Make sure that makes sense. All right, I think I'll pause here just so that I have more smaller videos than more bigger videos, and we'll come up with part B in just a minute.